Uh,
All right, good morning, everybody. So we continue our third day, and the first lecture is by George Sterman.
Thanks, Senator. So, good morning, and thanks for sticking around for the third of my lectures. Today we'll continue where we ended up. Let's just see what the last. Oh, this thing. Oh, yeah,
Sorry.
this needs to be connected in some fashion.
Again.
Okay. So we remember we wrapped up last time with a discussion about what the proton looks like from the point of view of the electron who's approaching with a friend, typically a single photon. And we had an idea as to why it makes sense to think of it that if there's a photon, there's only really one most of the time, and we can use that as an approximation to base our analysis. And in fact, that can be made through the magic of Feynman diagrams, of which we saw a little example last time, into something quantitative. So here's the topic, which is 5 of the 6 items. We'll see how we go through the hour. The EIC and the hidden world, strong interactions. And remember, right at the beginning, we talked about the hidden nature of the elements of the standard model, why it took till the 20th century, and then a good 50 years to really put together the pieces of the standard model, starting with the constituents of the nucleon, the up and down quarks, to see their presence revealed only by doing the kind of experiments we're going to discuss now. So it's the Alice in Wonderland picture through the looking glass into the micro world of the nucleon and nucleon. And that's what we're doing. This is again, going back to the first lecture, the emergent structure that mediates between the point-like quarks and the macro world. So this is just a selection of topics I'll try to touch on to try to put these topics, all of which will be discussed, I'm sure, in some already by Alexei, but others as the school goes on. The DIS valence distributions, a short review of perturbative QCD. And if we get through that, that's probably we can declare success. Transverse momentum distributions, excited nucleons, and the concept of duality, which is really very, very interesting. The original duality, actually, is a concept that occurs again and again in theoretical physics. Elastic scattering and nuclear radius, DVCS, GPDs, and nucleon structure. Well, it's too much. Okay. Well, DIS and transverse momentum distributions. So this is to make a long story short, and this is why QCD is such a big deal. It reconciled the irreconcilable. And here was the problem, as it appeared to people in the 1970s, around 1970, something like that. Quarks and gluons explained, well, okay, gluons, but quarks, basically. The quark model explained spectroscopy. So ions, QQ bar, baryons, QQQ, have different Qs, so you have different mesons and baryons. It'll work pretty well. Okay, but they're not seen directly. People were looking for them, and to some extent, they're still looking for them. And so that led to the concept of confinement, that somehow, so then the question is, are the quarks and gluons real? Are they just, it's like double entry bookkeeping or something like that, which is a good thing. Takes care of the budget. So the way things went in highly, which is deep inelastic, remember we talked about what could happen to a proton when an electron delivers momentum to it in a sudden way. Deep inelastic electron-proton scattering, the inclusive cross-section was found to be well approximated by the lowest order elastic scattering of point-like, and important point is spin 1/2. So we have predictions of scattering of point-like particles depends upon their spin. So this inclusive cross-section for deep inelastic scattering was well approximated by the lowest order elastic scattering. In other words, the absolutely quintessentially non-inclusive scattering of point-like particles. Inclusive of the bound state was like elastic of a point-like, of sets of point-like particles. And this result goes by the name of scaling. So here it is. And most of the equations we're going to write, we're going to look at will be of this schematic form. We have the inclusive cross-section, d sigma E plus P dq squared, which is a function of Q, the momentum transfer, P, which is the target, the proton mass, P dot Q. So big Q is, minus big Q squared equals little q squared, is of the form of a distribution, some function, which is a function of the variable x, the famous Bjorkheim scaling variable of q squared over 2p dot q, times this free or Born or lowest order elastic scattering for an electron on spin 1/2. And we would, this cross-section here includes the charge of the spin 1/2 particle that's scattered, so it's dependent upon how many quarks you have and their charges. Okay, so how many as a function of this variable x is given by this function here, which we can think of as in this schematic form, it's both a parton distribution and a contribution to some structure function. We'll see the structure functions in passing here, but this is not the level that I'm going in detail in this talk. Okay, so this is the big deal, and this is a huge big deal in applications of QCD. On the left-hand side, you have inclusive. On the right-hand side, you have elastic. This is where we start. This is the parton model. Perturbative QCD calculates corrections for this elastic scattering, giving more and more precise predictions for these inclusive cross-sections. However, there's a difference between the two factors on the right-hand side. One of them we can calculate here. We already knew how to do this from quantum electrodynamics. And when we go to more complicated processes, we'll use quantum chromodynamics. But this function f here is something that at this level we have to measure. And that's the way it was in the 1970s. Now we're finding out, in fact, how to use this method of correlations and the lattice methods to calculate these f's and check and look at them to see if our understanding and our methods are adequate. So here's the picture. And just let me, this is, yeah, okay. On the left-hand side, we have the proton coming in, and it's a big green blob, and then a photon arrives, and then a whole bunch of stuff comes out to some state x, okay? And we sum over all x. That's the meaning of inclusive. First we square it, and then we sum over all x. And here's our electron coming in, electron coming out. All we have to do is we prepare this, E of k. This, we know what k is because there was a big proposal to the government, and that in those days it was some millions of dollars, now some billions of dollars. And it gives you a beam, and a beam has an energy, and you design it to have that energy. And if you're successful, you really know what k is. Then you divide that total amount of money by something like 6, and you design detectors to see what E of k prime is. And if your detectors are good, you can measure this precisely. Then you know k prime minus k, which is q, actually minus q, if q is going this way. So you know how much momentum has been delivered to the proton just by observing the electron. It's an amazingly beautiful experiment. That's the reason why this inclusive cross-section only depends on the momentum transfer and the momentum of the proton here. Well, here are some familiar, fairly familiar formulas for kinematic variables that are often given in descriptions of deeply inelastic scattering or deep inelastic scattering. I won't dwell on them in this lecture. So Anything about this that somebody would like? I mean, what I really want to get across here in this particular slide is this difference between the left-hand side inclusive on a bound state and the right-hand side is exclusive on a parton, on an elementary particle. Now, why is this, and come back, why is this irreconcilable? Well, the problem is we have confinement. We know we're not going to get isolated quarks out of this thing. And yet the inclusive cross-section is given by scattering as though it were of a free particle. In other words, when we say it's a free particle, it's free from the strong interactions point of view. We know it's not free from the electromagnetic interactions because it scatters off, it absorbs the photon. Okay. All right, so that's where we are with this. Let's see what happens. Okay, so in words here, the I don't know, is this words? It looks like a picture. Okay. The inclusive probability or cross-section was found to be proportional. So here I'm reading just the inclusive probability was found to be proportional, here we go, to the scattering probability of free charged quarks. But the quarks never showed up in experiments. So how can a confined particle scatter freely? And that's, I mean, it's amazing how things fit together. That's when asymptotic freedom was discovered on paper. A theory such that if you probe it at shorter and shorter distances, it appears to be getting weaker and weaker. But if you probe it on longer and longer timescales, it seems to be getting shorter and shorter. This is in the language of the first form of the Schrodinger equation that we talked about. List of particles, what happens next? The rules, okay? And those rules tell you that if you look at very, very short timescales, the theory hardly wants to change at all. You have to wait some time for it to wake up. But once it's up, it's like, okay, now we're really going to get strong. And all of a sudden your picture breaks down and you have to go to another picture in terms of fields rather than in terms of particles. So here's kind of the explanation. And this blue, is this blue or purple? I don't know what color this is actually. This blue, right? At larger momentum transfer. Okay, the larger the momentum transfer, the smaller is the resolution. So X here is the fraction of the proton's momentum carried by the parton. And you find that, remember, we had a formula for X, which was Q squared over 2P dot Q. All you have to do is say P prime squared equals 0. That's the condition for elastic scattering. Here we say X times P, we're neglecting masses. So X squared, P squared is equal to 0. And then you demand P prime squared equals 0. That's the free elastic scattering. And that tells you what X has to be for that to happen. And that's what gives the formula we saw before, parton. So X is the fraction of the proton's momentum carried by the parton. DIS measures how partons share the nucleon's momentum. In the short time of the scattering, the quark is effectively free. But then lots of things happen. Confinement happens when the quark goes further away, the coupling starts to get large, the quark realizes there's a vacuum, it has to talk to the vacuum, it has to be confined eventually, but all that is too late to affect the, now, okay, the word affect, what do we mean here? To interfere quantum mechanically, the hard scattering at short distances. So we get a separation between effects that occur in a very short time and effects that occur over long periods of time. That goes by the name of factorization. Okay, so you hear about factorization, it's all about that. It's this question of quantum mechanical incoherence is the word we used. But it's something you have to go out and see if your theory is consistent with that. And the answer for QCD is yes. Not that that was so easy, but it wasn't so hard either. Okay. So the idea here is that we reconcile the irreconcilable by saying the free scattering is short distances, and then over long times, the confinement comes in. So they never get to interfere with each other. All righty. Let's go to the next one. So here, this is the basic example of a factorized cross-section. It's the product of a universal function, which we denote here f of x, meaning parton distribution, which we could also think of as lowest order as being the same as the structure function, with the universal f of x with a process-dependent partonic quark or gluon cross-section. We say process-dependent, well, it's different. I mean, first of all, if you're scattering a U quark versus a D quark, they have different distributions and their cross-section is slightly different. But also there are variations of this, which people realized right away. One of them is suppose you came in with a muon and you did this. So actually after the SLAC experiments, people did muon experiments at Fermilab and saw that they got the same basic things. Then you could also have situations which are a little bit more complicated and not as clean experimentally, but are so interesting. You could have a case where you send in an electron and instead of exchanging a photon, it exchanges a W. It takes its electric charge. So which W will it be? It will be the W minus. Okay. And out will come a neutrino. So now you want to say, oh, it's the dog that didn't bark. Okay. There is nothing. We don't see anything on the outside. But then if we look at our hadronic system, we say, yeah, there really was a hard scattering. Then we know we're seeing not what people call the neutral current, which are the gammas and the Z's, but the charge current, W's. These are the processes when people talk about process dependence, these short distance scatterings. But the distribution of partons in the hadron is supposed to be the long distance, and it's supposed to be in this language universal. It's supposed to be, and yes, I mean, so then one goes out and see, I mean, it didn't happen overnight. I mean, for those of us, any old enough to remember, data did what data do. They have statistical uncertainties, there's systematic effects. It wasn't entirely clear that the neutrino cross-sections, the charge current cross-sections were immediately giving these universality properties for the parton distributions, but over time, they did. And part of what made that happen was our growing ability to calculate the QCD corrections that address that elastic scattering, okay, imperturbative QCD, so which we'll get to. So, okay, and the beautiful thing about it is, of course, to emphasize this again, is that the scattering via photon, for example, or any other of these things depends on the spin of the quark. So this was the way that one had to saw that in these deep and elastic scattering experiments, they were happening by the scattering of spin 1/2 particles, just as in the parton model. It's amazing. Yeah, okay, I keep saying that, but it still is. It's okay. So here, the elastic scattering is just a single story in terms of quantum mechanics. It's just this, the scattering of a parton on the bottom with the electron on the top on exchange of the photon. And all the confinement is all the things that could happen after that. So what's the sum of all the probabilities of all the things that happen in the world, good and bad? It's a number. It's one of our favorite numbers. 1. It just adds to 1. Okay. Now, in quantum field theory, that has a name. That concept has a name, and it goes by the name of unitarity. And so one goes and applies unitarity and sees that the kind of obvious, what we're really doing is checking that the theory is self-consistent. So its probabilities have to add to 1. Okay, so yeah, and that's just a restatement. F of x is the quark distribution, a function of x, and also depending upon the spin and the flavor in the given hadron, it could be a proton, it could be a neutron. At JLab, you can set things up so that this is really happening on a pion through the so-called Sullivan thing process. So important corrections to this can be computed in principle. That's a little bit, we'll talk a little bit about this as we go along. So with these methods, we can describe both particles and jets in, well, this is kind of an older slide because it says 200 GeV at and 8 TeV. So these are just data of various kinds, especially for, so these, what we're introducing here very quickly are just the fact that you can, in the final state, you can say, okay, fine, this is good in the inclusive cross-section, but now I'd like to know single particle inclusive. Let me see a pion at a certain momentum, transverse momentum at a given, well, at a given transverse momentum, or I'll see a spray of particles, a jet of particles. These are things that in using different methods, we can calculate. For single particle cross-sections at RIC, for example, the range of agreement was a surprise for, and a great impetus actually for polar studies. So particle cross-sections require factorization into fragmentation functions and parton distributions. Parton distributions for the incoming, fragmentation functions for the outgoing. Jet cross-sections, we can calculate the final state interactions in jet cross-sections in principle, and we only need parton distributions for the initial states. But we have to be careful in how we define our jet events. And I don't know, that'll be certainly a subject of interest at the electron-ion collider in studies of hadronization. To first of all, to understand at the same time the calculable cross-sections of collections of particles carrying a certain amount of momentum, and then to try to understand the evolution inside those jets that produces the observed hadrons and the distribution of momenta and quantum numbers between the particles within a jet. So all of these things become accessible to us, but they're accessible to us through the same ideas that were first demonstrated in deep inelastic scattering. The separation of high energy scattering at large momentum transfer so that you know that the short distance scattering is really short distance, into a calculable short distance part and a long distance part that's universal and accessible through non-perturbative methods. So we're using both the perturbative and the non-perturbative in these factorized cross-sections, factorized precisely into perturbative pieces and non-perturbative pieces. And it's the consistency of those two that will lead us to the basic properties of these cross-sections, including evolution, resummation, and the like, which will just give a sketch as to how that works. Okay, so now that brings us kind of to this issue, factorization and its scales. So this is a very short course in perturbative QCD terminology and formalism, starting with collinear factorization, that is factorization in momentum fraction. I was about to say momentum transfer, but it's not, it's momentum fraction. And what, okay, what letter is momentum fraction in these slides? X, I think I heard it, yeah, X. I mean, it's just, you know, another voice. So here's the general form. This is it, everything in one. And as, of course, it's very, very limited, but it nevertheless is very general. We have physical cross-sections. Now, cross-sections, you say, oh, cross-sections generically have units of 1 over momentum squared because they're cross-sections, they're areas. So again, that's the area that the core electron sits there, and then all of a sudden this proton appears and it has a certain area. The electron can see what's happening at that, you know, that very instant, and it may know it may be at the edge, maybe in the middle, but there's an area which is effectively. So that's the cross section. So if it's within that area, something's going to happen. And that's why cross sections are a useful concept. So on the other hand, for simple analysis, which is what we're about to do, it's helpful to think of a function which is dimensionless. So you say, if I have a large scattering momentum, short distance momentum, so I have a large q squared, where q is the generic hard scattering scale. If I multiply q squared times sigma, I get something that's dimensionless, okay? And that's what we do. So that's the left-hand side. And always in these things, I want to emphasize, it's good to think of left-hand side and right-hand side, okay? And not the one's better than the other. They both have something to give us. The left-hand side is the thing we measure in one set of processes, and then we can start to predict left-hand sides, okay? And so we start by measuring left-hand sides, and we work towards predicting left-hand sides. On the right-hand side, we have a factorized cross-section. It's factorized into two pieces, a short distance piece, which I called omega SD, which is a function of the hard scattering scale divided by some scale that's for us to choose, which is denoted by mu. We can think of that scale, in fact, as being the renormalization scale. Very much what we were talking about yesterday when we drew that sphere and saying, okay, this is stuff that's shorter distance than this. We'll just sum over and we'll incorporate it to the extent possible into the scale, into the size of the coupling. So because we're going to, we have a dimensionless on the left, so we're going to factorize into two dimensionless quantities on the right. And we're going to have the short distance as a function of q over mu, and then alpha strong of mu. And then there's some f here, which I didn't emphasize at first. F is the thing that we want to compute. So the simplest thing is to think of f as every state in the final state that we can identify as having momentum transfer q, we weight it. We either say we count this state or we don't count this state. If we count it, f is 1. If we don't count it, f is 0. So then we say, okay, we count it. If we count all of them, then f is just 1. That's a totally inclusive cross-section. Well, we could do different things. We could say, let's look at the final state and let's see if we have evidence for strong energy flow in jets with much less energy flow between the jets. So we could count the number of things. And there's a whole ways of doing that, each of which each of which is discussed in the literature. Okay, so this omega, this long distance part here, rather short distance part, will depend on this same f, because this is the part that results from the hard scattering. And if you define f right, you can actually calculate this thing. Now, I should say the single particle inclusive, there'll be an additional factorization. But this short distance part is convoluted in terms of some momentum transfers with a long distance part, which we can think of as the product of two different, or one for deep inelastic scattering, one in hadron-hadron scattering, two momentum fractions. So an x and an x prime, whatever. So it's, and whoops, excuse me. There we go. Okay. And so here, the long distance part is convoluted in this x, and it must be a function of this mu, the same scale, because everything we didn't put in the short distance part, we have to put in the long distance part. And it depends on all the other mass scales in the problem. And we'll assume we're not going to worry about heavy quarks, which for the most part can go in here in this omega short distance. But we'll consider this, all the masses of the U quark, the D quark, the gluon, which is 0, and so forth. So we get this factorization. This is the QCD generalization of the parton model formula F times D sigma dq squared elastic, okay? And that d sigma dq squared elastic for DIS is just the first term in an expansion in alpha S. It's alpha S to the 0. And alpha S to the 0 is just exactly the description of the parton model, which says the partons act as though they're free. It's only when you start looking into the final state that you really need these with some F or something like that. Or if you do, as we'll see, precision experiments to see the Q dependence, that you begin to see the fact that the partons are interacting. So mu goes by the name of the factorization scale, and M is whatever infrared scale. And in fact, if you're talking about jet cross sections in certain cases, this M can itself be perturbed. Now, it's kind of interesting. I mean, if we're looking for things that are new, like new physics, like new particles, okay? Okay, well, how does that fit into this? Well, what happens is it's this game. We measure this in say, deep inelastic scattering. We do lots and lots of measurements in DIS. And then we calculate this omega SD in DIS to great accuracy, and we measure then these FLDs. Because we know this from experiment, we know this from calculation, and we determine what these Fs are. But these Fs are universal. So then we port the Fs over to another higher energy experiment, or one with more precision, or something like that, whether it be to the LHC on the one hand or Bell on the other hand. And then with a new set of things we can calculate, say in a new theory, in which they're super partners or something else, okay? Then what we do is we then have this part we know from other experiments, this part we compute for the new theory, and then we get a prediction for Q squared. So this is the whole program of high energy physics searching for new physics. It's using the results of lower energy experiments to get these universal factors and or lattice as the time comes, and then calculating short distance in the new theory to get predictions in the new theory. And then you go out and for the most part, you're disappointed because it's the same old standard model, okay? But, you know, time will come. Okay. So, all righty. So, whoops. Go back. Okay, so this is almost all collider applications. This enables us to compute the energy transfer dependence and different probabilities from in states to end states. So I wanted just a terminology which you may come across over time. This short distance function here, omega SD, is said to be infrared safe. Okay, and that's this F here. It depends only on the scales of the Hart scatter. The fact that the M, the infrared scales, are all in the long distance part and not in the short distance part. Up to correctness, that decreases powers of the momentum transfer. That's the technical aspect that we use in factorization, okay? And so it's here implicitly in the formula, but I wanted to emphasize it. And this infrared safety depends on how you sum over the final states. For certain choices of F, you'll get infrared safety. For other choices of F, you'll lose it, and you won't have any predictive power because M will move from here into both, and you won't be able to calculate either of the factors. And in fact, they won't even factorize the same way. Okay, so yeah, all right. So that's the concept of infrared safety. Infrared safety then enables us for the appropriate choice of mu to expand this omega SD as a perturbatively in powers of alpha S. And this is what we do. So how do we get to use this? Well, one thing about this is, you know, I said, oh, well, you know, we do calculate, we do some measurements, we get our Fs, okay, and then we can make predictions for new theories. Well, we also get predictions for the same old theories. And that's why we're able to make standard model predictions at the Large Hadron Collider and check whether or not there are signals for new physics. And the reason why that's a prediction is because at the Large Hadron Collider, the Qs will be much larger. And in fact, I mean, they're a lot larger. So if you think about the original SLAC experiments, momentum transfer of the order of a few GeV. Go to the Large Hadron Collider, it's TeV. So if you think that somehow it's really Q squared because it feels better, right? It's increased by a factor of 1 million. So it's really things change a lot. And in fact, if we go back to the, so just to give a sense of that, I think we can get it by going back here. You can see these are jet cross sections in particular. And you can see the range over which the cross section varies. Here it's 10 to the 13, the top of the scale. And here's 10 to the -1. So these are cross sections where we're getting predictions that vary over almost astronomical. Well, it's astronomical enough scales, okay? It's like a huge, huge range. And it's just amazing. In fact, when you think about it, we drew that little picture with the little sphere, and then does the wave fit into the sphere? Or does it not? We'll cut it off, and then we'll get a way of calculating by looking at graphs like this, the way the coupling will run. And so here, this here, the area, if you like, the surface area is changing by 10 to the 20th. But the same basic picture is holding the whole way. This has something to do while the world goes on. It is so stable in some ways. I mean, when you think of all the things that could happen. Okay, so anyway, so here's our factorization. Again, whoops. Here it is right here. And the statement is, wherever there's factorization, there's evolution. And this is the essence or a concept which is tied together with all of the analyses of different evolution equations, the so-called DGLAP evolution, the TMD evolution that Andre showed us in the last couple of days, and so forth. So then, here's how it works. We have this factorization scale. It says scale short, and that's like how we choose the radius of that little ball where we define our coupling. Wherever there's factorization, there's evolution, but this mu dependence here that helps us to separate the short and long. There's some arbitrariness in that, how we do it. But however we do it, the physical cross-section can't depend on mu. That's our choice. Okay. What we get out of it, we may not be able to calculate if we choose mu too small or too big, but it can't be a property of the physical cross-section. The left-hand side must be independent of mu. So therefore, so that's what the first line in red says. And then the second line in red says that, you know, this is a case where we have separation of variables because we have dimensionless ratios on the left and right of this equation here. Here, mu appears in on the short distance part is q over mu, and then in the coupling alpha s of mu. And here it would appear as mu over m, so it's independent of q. So now what that tells us is that the mu dependence of f, the long distance part, has to cancel the mu dependence of the short distance part. Okay. So all of a sudden, we know how to go from one scale mu to another scale. The only variable they hold in common is alpha s of mu. Okay, so this thing I've denoted, P of alpha s of mu, is a separation constant. It's exactly the technique that one uses in solving the the Schrodinger equation for the hydrogen atom, something. Okay, and so now this is actually beautiful, okay, because if you know omega at first order in alpha s, all you have to take is mu d by d mu, and you get this P of alpha s. And so therefore, this P is calculable by looking only at short distance quantities where you trust perturbation theory. But yet, that gives the mu dependence of the long distance theory itself. Now, okay, so what's going on? Why does this magic happen? It's because of that picture we had in terms of virtual states and times. The proton's coming along. Remember, we had the picture that little lines going each and every way, and it's going through various states. And the states live for lengths of time that depend on how much they violate the conservation of energy. When we come in with a very, very large momentum transfer, say Q1, we'll see states that live up to the time scale 1/Q1. Okay. Then we come, okay, we get another $1 billion, we upgrade the energy, we have Q2. We can now see states that are up to times 1/Q2. So you say, okay, so you can see a few more states. But the thing is, just the counting we did yesterday, there are many more states at scale Q2 than there are at scale Q1. If you increase, generally the number of states increases like, the cube of the scale. And so you double the energy, have the time, you get 8 times as many states. So not only will you get to see these shorter lived states, you will mostly see the shorter lived states at the higher momentum transfers. And it's this little equation here, suitably interpreted for the processes at hand, that enables us to quantify this. And we just solve this equation we can solve for the mu dependence of both omega and F in terms of the mu dependence at a smaller scale, and we get the generic form like this. Now, sometimes, as Andre showed us yesterday, we have two factorizations going on at the same time, and then we can get 2 integrals, and we get Sudakov resummation. But I hope I've given you a sense of how the thing works. To some extent, also physically, of why it works this way. In terms of the scales, the two statements, larger momentum transfer goes to smaller scales, and then there are many more states that live at smaller scales than there are states. No, there are many more states that, live at smaller scales than at larger scales, just because of the volume of the phase space. Okay. So in collinear factorization, this is just going over the absolute basic results in DIS structure functions, for example, F2. There is a formula here that defines the structure functions in unpolarized scattering. So it equals a sum, or there's an implied sum over parton flavor A, and there are so-called Wilson coefficients here, C's, which are functions of Q squared over mu squared, alpha S of mu, and then we have our distributions as a function of mu. But notice, by the way, that although this kind of like analysis is very, was very schematic, the idea that these F's, these little F's, they're if you're doing collinear factorization, they're universal among all such properties, all cross sections that enjoy collinear factorization. And so once you have those P's, you can apply them to any. The F evolution is in this sense universal. This is DGLAP evolution, it's often referred to. And here is just to remind us, if you perhaps have seen this before, this kind of convolution here. So that was that O times with a circle represents an integral like this. In the case of DIS structure functions, they factorize into moments under products. And so if you happen to know the P's as a function of alpha S, and say at just the lowest order here, this is gamma N1 is some coefficient, which depends upon this N, the moment that we took, the Mellon moment. Then we get these beautiful expressions, which are predictions for the nth moment of the structure function. And then if you do this integral, you go linear in alpha S goes like 4 pi over log mu prime over lambda d squared. Okay. Oh, yes, I did. I actually put it in there. I even remembered 4 pi, but I forgot the B naught. Okay, so and that's 11/3 minus something. Okay. Anyway, so you get this kind of prediction for are taking our structure functions, measuring them some Q naught squared, taking their moments, and then you get a prediction for the higher Q squared. Well, higher or lower, it really actually doesn't matter. I mean, this works as long as these logs stay large enough. Of course, I mean, as the ratio in the log stays large enough. When the ratio approaches 1, the log tends to vanish, and then that's where your perturbative theory is breaking down. And it's breaking down not totally mysteriously. You can see that it's individual expansion. Every term is giving the same answer. Okay, so this is the basic application of factorization and evolution. So, yeah, I mean, in DIS, a beam of electrons is a machine for detecting quarks. So that's what we're going to do, quarks, and then indirectly detect gluons from the fact that gluons produce quark pairs. And so here was just an example of large X distributions. I mean, basically, I probably said everything I can say with hope of getting something across. Let's see what else there is. I mean, this shows examples from recent experiments of actually, now this is really interesting. Okay, here's this X, and these are these structure functions as a function of X. And you see here in these recent experiments, there's data all the way out almost to X equals 1. I mean, these are very, very difficult experiments. And this really enables us to test QCD in another region. So as you go to X equals 1, what happens is you have a new scale, a dimensionless scale, 1 minus X. And so logs of 1 minus X appear. In fact, log squareds of 1 minus X appear. So the simple analysis I gave before is still right, but there's a hidden scale in there that we didn't talk about, which may favor or emphasize or de-emphasize certain portions of the convolution, and you have to do other analyses, which one does. I mean, and you know, it really does work well. I mean, this is the kind of result. These are from Hera, and if anything, the data has actually gotten better and through the advanced analyses since the Hera was closed down about 20 years ago now. What you really see is this evolution. So the scaling that gave people confidence that asymptotic freedom was the way to go, and you needed a theory with asymptotic freedom. That's what you should spend your time analyzing and comparing to experiment. It really paid off. It also represents one of those felicities in experiment. Back in the days when the experiments were being done at SLAC, here's Q squared, and here's F of X for different X's. And the X's and the Q squareds were all kind of in this region here. And scaling is the statement that F is independent of Q squared. And here it's flat as hell, you know? So people said, my gosh, scaling, the quarks are free. The quarks are free, you know? But they're not so free. It depends on where you look. It's like all life is constrained, and physics no less. And when you go out to these, to these smaller X's, you see a tremendous Q squared dependence. And all this Q squared dependence in here is predicted by these little formulas. Formulas as simple as this. And then, okay, you go to the next loop, it's a little more complicated, but still, it's this basic observation that gives us the I do. As we get the light.
Doesn't want to switch.
Here we go. Okay, yeah, good. That gives us this kind of experimental success. And this is why people have confidence in taking these things to the Large Hadron Collider. And also gives confidence in the worthwhileness of generalizing this formalism in terms of the fractional momenta, collinear momenta, to these more detailed properties of TMD distributions and generalizations to generalized part-time distributions, things like that. Because we're on a winning streak. I mean, we're doing great. Okay, so similar analysis applies to all the structure functions, and here are the QCD. I promised that before. We see, okay, so this is, all right, we have this thing, the hadronic tensor, W mu nu. So this is the whole deep inelastic scattering cross-section in the one photon approximation in terms of matrix elements. We start out with some P and momentum P, spin S for our proton. We see the action of the electromagnetic field. We produce states X, we square it, we sum over X. That's just quantum mechanics. We divide by 2 pi because it's always a good idea to divide by 2 pi. And now here, actually, there's so much history in this formula itself, this definition of the hadronic cross-section. This is everything that was not understood about deep inelastic scattering, but it makes a huge well, it's an approximation, which is the one photon approximation, but it makes a big assumption about the way that the strong interactions work. It says the strongly interacting particles in the size of the proton interact with the photon at a point-like operator, which we can describe as the electromagnetic current. Okay, and that's J mu of 0.0, but J mu of X or J nu of X. Now that is actually an assumption. It's an assumption that the strong interactions are defined by local quantum field theory. And that assumption was made in the analysis of deep inelastic scattering before the SLAC was built and led to various formalisms that enabled people to identify the importance of scaling and to identify and to analyze the cross-section in a manner similar to what we've just discussed. So it's really one of those huge things. It's a choice that people made. Let's do it this way and see what comes out. And of course it came out. All right. So, the structure functions, there's F1 and F2 for the unpolarized, and then of course of great interest in the EIC are the G1 and the G2, which just like Andre was showing, they have spin dependence, but notice how simple the spin dependence is. It's always just linear. You can't have spin floating around and dotting spins into other momenta just at random. It's very simple. All righty. So, how much spin parsons carry? Parsons don't carry any, partons carry some. And here's the spin dependent distributions that were known a few years ago. There's some improvements in some. So, so this kind of, I'm coming to the end because I'm running out of steam here, actually. But and I think all of the foregoing looks inward towards the hard scattering. Okay, so that's what we've been talking about. We remember our motivation is seeing that whole part proton with all the guys running around inside. So, but for a long time, the emphasis was the verification of QCD at the shortest distances, prediction of new physics signals at high energies. The path to a fuller understanding of the theory, which is what the EIC is all about, is looking away from the hard scattering. And there are two qualitative ways we can think about that. Far back into the initial state, before the collision, the structure of the nuclei and the ends, say the nucleons and nuclei beyond that in the language of particles. And far forward into the final state, after the collision, hadronization. These two features at some level factorize, but to do those factorizations, we'll have to have new sets of experiments. And that's what this school and what the whole EIC program and the current Jefferson Lab program are. The questions we seek to answer will still be phrased in the language of hadronic structure and formation in terms of partonic degrees of freedom. And okay. So here are some of the things and the concepts that come in handy. To start, well, to start is the Big Bang, but okay, to start over short time scales, the quark doesn't have to be moving in exactly the same direction as the proton, but it does on average, right? Because, protons aren't, where's that quark? Oh, there it is. Okay, I'll go back and get it. No, protons don't work that way. So on average, okay. Other measurements, say single inclusive deep and elastic scattering, are sensitive to this extra motion and transverse momentum distributions, or TMDs. So these cross sections factorize too into parton distributions and fragmentation functions that depend on extra transverse motion of the quarks and gluons. So it's the same principle as before, omega short distance, circle times long distance, but the circle times is now a little bit more complicated. Now, this statement that they factorize is a statement that depends on the process you're putting. It's not true for every statement. If you start looking at very, very detailed questions in the final state, we'll lose this separation of the transverse momentum distributions from the rest. I mean, basically, it's like this. If what you have to do is to find something where you say, okay, the quark is scattered with a certain transverse as well as longitudinal momentum. So it's sort of like that, And then you look at something that depends on this momentum, but doesn't depend on the recoiling transverse momentum of the remainder of the proton. So that's kind of a subtle thing. And that's why the factorization gets a little bit trickier in that case. It doesn't always apply, particularly in cases when you have two incoming hadrons and then you're looking at partons in the final state. Okay. So here, corrections here are even more important and all double logs, but they can still be computed in principle. With electron scattering, we can measure the momentum fractions of quarks, their transverse variations, and how their spin is connected to the spin of the proton and their transverse. This gives a family of functions to measure, and together they demonstrate the full correlation of single quarks to the momentum and spin of the proton. And I probably have one of those diagrams here. Well, yeah. Okay. So here's a QFT expression, all right, for these transverse momentum distributions. And the picture is a little bit, I think you've heard these words said, Andre said more or less the same thing. We have a matrix element. We start with the proton. Here it is, the initial state, P and S. And now this isn't a particular gauge, but let's not worry about it too much. We have a quark field here, psi Q, particular flavor, sitting at this point psi along the light cone. And what happens is the photon scatters the quark here. This quark, which is scattered, disappears from the story. Okay? And that's the statement that we're not going to worry about correlations between that transverse momentum and the transverse momentum of the spectators, the rest of the remnants inside there. And then, after some period of time elsewhere along the light cone, or some period of light cone time, the quark reappears and forms the original state. And then out of all of these matrix elements, we take this Fourier transform in terms of transverse momentum, transverse positions, and light cone positions. And it takes this structure of a spin-dependent piece and the spin-independent piece. And this is just what we saw. So this is just, I wouldn't call it straightforward generalization, but in any case, generalization. And yeah, then there are in the remainder of this talk a number of really interesting things. Let me just emphasize this. One, electron-positron scattering to excited nucleons for intermediate momentum transfers, so not too big, not too small. We compare this, which is our factorized cross-section, to the production of heavier, unstable versions of the proton. So not just one in this case, but all the quarks are scattered together into some excited state. And yet the two probabilities, this one based upon only the scattering of a single quark, factorized cross-section, and this one, which is just a hadronic description or phenomenological description in terms of resonances, are closely related. And these are the so-called quark hadron duality plots or Bloom-Gilman duality. Going historically, it was something that was noticed way, way back around at this time that scaling was first observed. The fact that when you look in detail, you see that what the perturbative picture gives you is a kind of average. And the average doesn't depend on what happens late in times. So it's very pleasing to think of it this way, I think, that you get the scattering, that's the scattering of the parton model, and it gives you a certain probability distribution. And then the very, very long time scales redistribute the probability distribution from a smooth curve into some peaks, valleys, peaks again. And this has been, this is derivation. Well, this is a recent review, relatively recent review, but really a lot more has been done from the experimental point of view. Then there's the nuclear radius. Maybe somebody will talk about it, but this hopefully will be settled the time the EIC is built. Exotic states, glue walls, people study that, as you know. And then deeply virtual Compton scattering and generalized parton distributions, where you take the picture of deep inelastic scattering and you turn it into an amplitude. But not quite the same thing. So again, DVCS, you start out with a proton, you come with an off-shell photon, something happens at short distances, an on-shell photon is emitted, and the proton goes its merry way with a small momentum transfer. And this leads us to the idea of looking not just at a single point or parton, but to actually looking at the extended structure of the nuclei. And you can do that, and let me just show, I'll skip all this. So now you've seen these, all the distributions that's necessary to describe the various aspects of QCD and proton structure we've discussed. And so here's where this is what DVCS looks like in some sense. Step one, the electron exchanges a virtual photon with the quark. So here it is. The quark's over here. Here's the electron skirts by. It says, here, take my photon. And so the quark does. The quark travels some distance, re-emits another photon. The photon escapes, but the quark remains in the proton, which now has a different total momentum. So it redistributes its momentum and the proton goes its merry way. And all this varying the spin of the electron and or the proton gives information on the spin of the quark. It's given a family of generalized parton distributions, which are based on this rather simple picture here. And it's kind of the picture we had for the structure function. The quark disappears, all hell breaks loose, but then suddenly the quark reappears and the proton comes out with the same momentum. In these beautiful sets of experiments, which are being done, you can actually, this is the picture that we see as what these test. And for the rest, there are a few other topics, but I think this is an okay place perhaps to end this lecture after an hour. So thanks.
Some comments.
Oh, that's great. Let's go get coffee. He'll ask you questions in there. Oh,
I have a few, but for lunch.
okay.
Or I can ask them now.
All right, ask one so that we don't go questionless.
Okay, so we have the world of quarks and world of particles. As you mentioned, for instance, the process of hadronization is very interesting. The quarks, don't observe them in experiments, so particles. Okay. So now if you look, say, about the unitarity for both theories, they would look differently because you have different Fock spaces. for one theory or the other. Yet we employ ideas about I'm being provocative here, okay? It's not that. Yet what we say is that there is some way to connect one to the other. That's what we see. Experiment does, and through 14 orders of magnitude predictions of perturbed QCD shows that it works very well. On the other hand, if you, for instance, look at a very simple interpretation of permutation function, for instance, have a vacuum state, work operator, and then you have your hadrons that you produce. Okay, so now work operator acts on the vacuum state and creates a state in the Fock space of your QCD theory, which is quark, free quark, which has fractional charge, and it has to overlap with the Fock space of your hadronic theory, where particles don't have fractional charge. How come this thing overlaps?
Well, these are, that's the reconciling the irreconcilable part that we had before. So how does it really work? Of course, we don't know the answer. But I think the way to think about it is that you can invoke this magic phrase of effective theories that on different length scales and times, different degrees of freedom are more effectively describing what's going on. And we can see that by starting out with the simplest example that we gave, the fundamental degrees of freedom. We say they're fundamental because we can write down Lagrangian and we know that there are no more terms. And then we have rules for how states will develop through time, through the emission, absorption, changing the list of particles that we have. We also see that that picture fails when we try to make that time too large. Now, on the other hand, you can say, well, gee, that hardly leaves us any time at all to do anything. But you see, that's what's beautiful about those data, for example, for jet cross sections. They're hardly the whole thing, even the lowest scales are tens of GeV. So they're already fractional fractions of a Fermi. And by going to higher and higher scales, we're looking at time scales even shorter than that. So we're taking, instead of kind of making X or T large, we're making 1 over T large. And we test it by making it very, very large. But when we keep increasing T, 1 over T gets smaller and smaller, eventually we can't self-consistently compute the time evolution of the system. Beyond that, we have theories or phenomenological pictures of what goes on. But of course, eventually we get something like chiral effective theory, where our momentum and the times involved are like 1 over the mass of the pion or even longer. And there we have a very, very good picture. So nobody has yet found a way of, really smoothly, from a conceptual point of view, connecting these things. We found techniques based on factorization, which put all the difficult questions into some non-perturbative functions, or which under certain circumstances, you're beginning to be able to compute on the lattice. And so we've made a huge amount of progress. Everything is consistent with this picture of, well, the real thing is not our description of it, even in terms of the fundamental degrees of freedom. The real thing is all this, all at once. I mean, it's almost mystical. It's like not maybe healthy to think about things this way too much, but we'll keep chipping away is all I could say. We may need some really new ideas as to how to bridge this kind of gap. And
well, I'll ask this question because actually, well, my dream for the electron ion collider, for me, is to be able to tag on the mediator between the two worlds. So what it is that, say, creates a particle out of the quark, because at some point there should be something which is not a quark and yet not a hadron. So it's not happening like this. Maybe it happens like this. Maybe it's a
Well, it
method, but
depends
should
on
be-
how you're looking at it. If you look in terms of 1/t, it's maybe like a little thing, but when we look in terms of momenta, it's all happening 2 GeV to 1 GeV, it's all over. You know, and to some extent, I think we were a little naive in thinking, you know, with the energy range of Jefferson Lab, we'll see quarks turn into hadrons. It doesn't happen that way.
That's exactly.
But it may happen, but it happens some way. And we may find a set of experiments and observations, which does what Andre suggests we should see.
The ignorance is high. I even don't know yet how to define this thing consistently. Maybe you'll find a way. Okay. All right. Any other questions or comments? Or do you want coffee immediately? They want coffee. Let's thank George.
Yeah.
That's thanks, John.
Yeah, this is.
We'll just go to the sculpture.
No, it's interesting, you know.
You mentioned amazing. That's exactly what we are working on. One is threshold estimation for functions. Because that, I think will allow us to actually
When he brought it up,
the agreement.
reminded me.
1 minus x is that. And the other thing is
It's
amazing.
like,
You have
it's pretty interesting. Now.
so
Because I guess you'll
and perhaps future. Find out what is this like curve, because it's not quite known. There are lines there. Yes, there are no.
How should you, I mean, you're pushing it to scales where it's
Exactly. So what is this curve? Can we really?
There are various waves, there are different directions.
Probably
And
some those
for those,
resonances.
like
Right.
when you discretize the.
Is it happening? There are many resonances that create this smooth curve out.
Making
So you understand the nature. One can see it on smooth distribution function.
Yes.
One can
You
think
do it,
about
you
S channel.
I think generally it's you and me, illustrator.
That it stays in S channel.
Right.
I was doing
process.
theory.
Yeah, so-
In the previous.
These
duality,
Duality just
duality.
it makes sense.
I have no idea.
Just amazing. Thank you.
Probably got
Nice.
the
Oh, thank you very much.
chips, you know, combination.
Speaking now, I mean,